Hello there, welcome to the Engineering Mechanics video lectures. In this video lecture, we are trying to see angular motion or rotation of a rigid body about a fixed point. So here what will happen, this is the rigid body, it's going to be taking a rotational motion with respect to a fixed point. Then we can say that is going to be the rotational motion of the object. So for the time being, I am going to be considering a rigid body. It is going to be in this shape. So any one arbitrary shape R can take, or I can say this is going to be a rigid slab, I can say. So then for this one, I am going to be taking the central axis of the member. So then in this case what will happen? I am going to be considering here the 2 points I can take it. One is going to be your fixed point. The second one is going to be the point P, where we are keeping our observation and we need to find out the behavior of this object. So for this part, I am going to be taking here, this is going to be the O, right? The O is going to be your fixed point on a rigid body. And next, the point P I am going to be considering over here, right? So the distance between the P and the O always constant, even though the force is going to be applying on this member, because we are considering that is a rigid body. So then what happened next? When the force is going to be applied on this member, then the member is going to be subjected to the resultant force and it's trying to move in the same direction. That means object already it is fixed, this PO is going to be the constant, and then I'm going to be taking one horizontal axis, this is going to be the X suppose. So then it's trying to move towards like this, right? And it's trying to move in a circular path. So then I can say this angle I can consider as a theta, right? In this case, the theta is looking 90 degrees, but if you are going to be taking a little incline to this, then there is going to be a theta is going to be existed over there. So then it is occupying the new position Q. Can you see? O is going to be the fixed point and this is going to be your observation point. When the applied force applied, so then what will happen? This object is going to be trying to rotate it. So the best example is going to be the gear blank or a pulley, which are using to transmit the forces from one point to the another point. That means the power transmission is going to be taking. So can you see? So I am going to be taking a gear blank over like this. So can you see? So roughly I am going to be draw the teeths like this. So then what will happen? This gear blank is going to be fixed on a shaft and they are going to be making to rotating. So this is also called the rigid body, but for our time being I have taken like this, right? And now we are going to be find out the different parameters on this part. Can you see? The theta is going to be called your angular displacement. Angular displacement. So the P is going to be your initial position and Q is going to be the final position, right? O is going to be the fixed point. So now can you calculate the angular velocity for this object? Now I am going to be calculating the angular velocity. So how to calculate the angular velocity? So in this case what will happen? Angular velocity is nothing but the rate of change of angular displacement we are going to be calling your angular velocity. That indicated letter I am going to be say the omega. The rate of change of angular displacement. Here is the angular displacement is going to be your theta. That I am writing d theta by dt, because we are saying that is going to be rate of change of angular displacement. That means rate of change of with respect to time we are considering. So that's I am going to be say radians per second. In this case, the angular displacement always we are measuring with. So here we are measuring with radians, alright, the radians. Now this way we are going to be calculating the angular velocity. Once we are going to be calculating the angular velocity, can you calculate the angular acceleration? So that I am going to be writing over here. So that's going to be angular acceleration. So in this case, angular acceleration indicated letter is going to be the alpha. The definition of angular acceleration is the rate of change of angular velocity with respect to the time. Then we can say that is the angular acceleration. In this case, the object is going to be trying to rotating with respect to the fixed point. That's why we are getting angular displacement, angular velocity and angular acceleration. If a particle is moving in a horizontal direction, in a linear direction, then that object will going to be getting the linear velocity, linear accelerations we are going to be considering. So now alpha is equal to, what is the formula? The rate of change of angular velocity. Right, the rate of change of angular velocity, that is going to be d omega by dt I am going to be considering, right. So then we can say this is going to be d omega. So for this one, d by dt is into d theta by dt also I can take it. So the final equation of the alpha I am going to be getting d square d theta by dt square I can get it. Can you see, this is the simplification of your angular acceleration that I defined in terms of your angular displacement. In this case, I was defined in terms of the angular velocity. Once we are calculated the angular velocity, angular acceleration, now we can see when this object is going to be rotating with uniform velocity, the uniform angular velocity and uniform angular acceleration. So then what is the behavior of the system? We will calculate it. So the next condition is that uniform angular velocity. Right. So in angular velocity, omega is equal to, we got it d theta by dt. Can you see, in this case the omega is going to be uniform, means the particle or the rigid body is going to be covering with uniform distance in interval of time. Right. So then these equations we are going to be simplifying, and to find out the uniform angular displacement we are going to be calculating. That's going to be d theta is equal to omega into dt, right. If I am going to be simplifying, it is covering only the uniform displacement, then theta is equal to omega t I can say. So the theta here is going to be uniform angular displacement, then automatically this angular velocity will become uniform angular velocity. So we are going to be calculating, and similarly uniform acceleration also there. Uniform angular acceleration. So this equation how we are going to be calculating. See, in this condition, uniform angular acceleration. So uniform angular acceleration formula we know, alpha is equal to d omega by dt, right. I need to find out this part, d omega is equal to alpha into d theta. And further simplification of this equation, I am going to be integrating 0 to omega, d omega is equal to 0 to t alpha dt, right. If I am going to be simplifying this equation, I am going to be getting here omega is equal to alpha t plus c1 I am going to be getting. So in this case, the C1 is going to be the constant. So we need to be find out. So if you want to find out the C1 constants, initially we need to submit initial conditions. What are the initial condition? What is the initial angular velocity? Right? That I am going to be taking omega naught is going to be your initial angular velocity. Right? When this initial angular velocity, the t is equal to 0. That's going to be time is equal to 0. So once if I am going to be substituting in this equation, that this omega will become omega naught, right? And here is going to be the t will going to be 0, that is equal to alpha into 0 plus c1. So from this equation I found it, c1 is equal to omega naught. Omega naught is nothing but your initial angular velocity of your rigid body when the time is equal to 0. Now the C1 values I am going to be substituting in this equation. So that I am going to be getting omega is equal to omega alpha t plus omega naught. So can you see, by this way we are going to be calculating the uniform angular acceleration in terms of your angular velocity at the final and initial angular velocities we are going to be calculating. Now I will try to correlate between your linear parameters as well as the angular parameters, so that you can understand better. So now we do have the two conditions, one is the linear motion and rotational motion. Just before we have derived, that's going to be omega is equal to omega naught plus alpha t. If I am going to be taking for the linear motions, so then the same equation, the final velocity is equal to initial velocity of the rigid particle plus uniform acceleration A with relation to time. So can you see the comparison between the linear motion as well as the rotational motion of a rigid body? And there is another equation we do have, that's going to be v square is equal to u square plus 2as. In this case, all our terminologies will come uniform velocity and uniform acceleration. When I am going to be writing for the rotational motion, this is going to be coming omega square is equal to omega naught square plus 2 into alpha into theta. So in this case, S is going to be your linear displacement of the system. In this case, theta is going to be uniform angular displacement of the system. So then we get, and another equation, S is equal to ut plus half a t square formula we do have. From this one, we are going to be calculating the distance covered in respect to time we are going to be calculating. And similarly, we need to be calculate for the rotational motion. What is the value? What is the equations? We can modify this equation. Here, S is going to be your linear displacement. When it comes to here, there is a angular displacement is there. That's going to be theta is equal to u is nothing but your initial velocity here, initial angular velocity into t plus a is going to be your angular acceleration, that is going to be linear acceleration that I am taking here 1 by 2 alpha, and the t square I am going to be writing here as it is. The time is going to be the same. So can you see the comparison between the linear motions as well as the rotational motions? So this way we are going to be calculating, right? So now we will see what is the linear motions as well as the rotational motions in one equations, how they are going to be identified or that tells the behavior of the rigid particle. So in this case, the linear angular velocity, linear angular acceleration in rotation, how they are going to be existed. So for this one, the resultant acceleration I am going to be writing, the resultant acceleration A is equal to an plus at I am going to be taking. What is the an here? The an is nothing but normal acceleration, at is nothing but your tangential acceleration. Already we have derived this equation in the previous video lectures in terms of this kinematics of a particle. So that I am going to be writing an, I am going to be writing v square by r, I can write it, right? That is what we have seen. So plus at I am going to be writing dv by dt, right? So if I am going to be simplifying this equation, what I am going to be taking, v is equal to omega into r, we do have formula, that's already we derived. This equation I am going to be substituting in this part. So then A is equal to, what is the formula here? That's going to be omega into r whole square by r. Can you see? V square is nothing but your angular velocity into the radius we are taken, plus d into dt into omega into r we are going to be considering. In this case, r is going to be the always constant. It is going to be fixed part, suppose. So then what will happen in this case? So omega into r square by r, this r will going to be cancelled. I am going to be getting omega into r plus, in this case r is going to be the constant that I am going to be taking this side r. This d omega by dt is going to be your, what is the value we are going to be say? That is going to be alpha I am going to be talking. So in this case, r square, omega square, r means here is r is getting, this is going to be the square, we will get it, and this omega by dt is going to be alpha. So then finally the acceleration in the rotational, this is going to be your, the resultant acceleration A is equal to r omega square plus r alpha, I can take it. So this way we can calculate it. In this case, the linear angular velocity, linear angular acceleration in rotation, how it is going to be existed. I hope you are able to understand what is the exactly this angular motion or rotation of a rigid body about a fixed point. That's already we given the example of that. There is a gear blank is there. Then it is taking the angular displacement. Then we have calculated the few parameters like angular velocity we do have taken. So how we calculated the angular velocity? So here angular velocity omega is equal to d theta by dt, I can take it. And similarly angular acceleration is equal to d omega by dt, I can take it. Alright, then we do have uniform angular velocity. So uniform angular velocity, that's going to be the theta is equal to omega t we have calculated, right? And similarly alpha also we have calculated, that's going to be omega is equal to omega naught plus alpha t, right? And then we have developed the relations between the linear as well as the angular motions. So further we are taking in a single equation, so that's we got it. The resultant acceleration is equal to r omega square plus r into alpha. So this way we have derived these equations. They are same helpful to find out the different parameters like any of this angular velocity, angular acceleration or the displacement, angular displacement also we can calculate it. I hope you people are able to understand what we have discussed over there. So still you feel any difficulty or any confusion regarding this concept, please put in your comment section so that I can helpful to you to solve that your problems. So thank you. Please subscribe to the channel. Thank you.